Electric charges and fields. Introduction. All of us have the experience of seeing a spark or hearing a crack when we take off our synthetic clothes or sweater, particularly in dry weather. Have you ever tried to find any explanation for this phenomenon? Another common example of electric discharge is the lightning that we see in the sky during thunderstorms. We can also experience a sensation of an electric shock either while opening the door of your car or holding the iron bar of a bus after sliding from our seat. The reason for these experiences is the discharge of electric charges through our body which were accumulated due to rubbing of insulating surfaces. You might have also heard that this is due to generation of static electricity. This is precisely the topic that we are going to discuss in this and also in the next chapter. Static means anything that does not move or change with time. What is electrostatics? Electrostatics deals with the study of forces, fields, and potentials arising from static charges. Electric charge. Historically, the credit of discovery of the fact that amber rubbed with wool or silk cloth attracts light objects goes to Thales of Miletus, Greece, around 600 BC. The name electricity is coined from the Greek word electron, meaning amber. Many such pairs of materials were known which on rubbing could attract light objects like straw, pith balls, and bits of papers. Many such pairs of materials were known which on rubbing could attract light objects like straw, pith balls, and bits of papers. It was observed that if two glass rods rubbed with wool or silk cloth are brought close to each other, they repel each other. The two strands of wool or two pieces of silk cloth with which the rods were rubbed also repel each other. However, the glass rod and wool attracted each other. Similarly, two plastic rods rubbed with cat's fur repelled each other, but attracted the fur. On the other hand, the plastic rod attracts the glass rod and repels the silk or wool with which the glass rod is rubbed. The glass rod repels the fur. These seemingly simple facts were established from years of efforts and careful experiments and their analysis. It was concluded after many careful studies by different scientists that there were only two kinds of an entry which is called the electric charge. We say that the bodies like glass or plastic rods, silk, fur, and pith balls are electrified. They acquire an electric charge on rubbing. There are two kinds of electrification, and we find that like charges repel each other and unlike charges attract each other. The property with which differentiates the two kinds of charges is called the polarity of charge. When a glass rod is rubbed with silk, the rod acquires one kind of charge and the silk acquires the second kind of charge. This is true for any pair of objects that are rubbed to be electrified. Now, if the electrified glass rod is brought in contact with silk, with which it was rubbed, they no longer attract each other. They also do not attract or repel other light objects as they did on being electrified. Thus, the charges acquired after rubbing are lost when the charged bodies are brought in contact. What can you conclude from these observations? It just tells us that unlike charges acquired by the objects neutralize or nullify each other's effect. Therefore, the charges were named as positive and negative by the American scientist Benjamin Franklin. By convention, the charge on glass rod or cast fur is called positive and that on plastic rod or silk is termed negative. If an object possesses an electric charge, it is said to be electrified or charged. When it has no charge, it is said to be electrically neutral. A simple apparatus to detect charge on a body is the gold leaf electroscope. It consists of a vertical metal rod housed in a box with two thin gold leaves attached to its bottom end. When a charged object touches the metal knob at the top of the rod, charge flows on to the leaves and they diverge. The degree of divergence is an indicator of the amount of charge. Try to understand why material bodies acquire charge. You know that all matter is made up of atoms and are molecules. Although normally the materials are electrically neutral, they do contain charges, but their charges are exactly balanced. Forces that hold the molecules together, forces that hold atoms together in a solid, the adhesive force of glue, forces associated with surface tension, all are basically electrical in nature, arising from the forces between charged particles. Thus, the electric force is all pervasive and it encompasses almost each and every field associated with our life. It is therefore essential that we learn more about such a force. To electrify a neutral body, we need to add or remove one kind of charge. When we say that a body is charged, we always refer to this excess charge or deficit of charge. In solids, some of the electrons, being less tightly bound in the atom, are the charges which are transferred from one body to the other. A body can thus be charged positively by losing some of its electrons. Similarly, a body can be charged negatively by gaining electrons. When we rub a glass rod with silk, some of the electrons from the rod are transferred to the silk cloth. Thus, the rod gets positively charged and the silk gets negatively charged. No new charge is created in the process of rubbing. Also, the number of electrons that are transferred is a very small fraction of the total number of electrons in the material body. Now we are going to study about the conductors and insulators. Some substances readily allow passage of electricity through them, others do not. Those which allow electricity to pass through them easily are called conductors. They have electric charges, that is, the electrons, that are comparatively free to move inside the material. Metals, human and animal bodies and earth are conductors. Most of the nonmetals like glass, porcelain, plastic, nylon, wood offer high resistance to the passage of electricity through them. They are called insulators. Most substances fall into one of the two classes stated above. When some charge is transferred to a conductor, it readily gets distributed over the entire surface of the conductor. In contrast, if some charge is put on an insulator, it stays at the same place. You will learn why this happens in the next chapter. This property of the materials tells you why a nylon or plastic comb gets electrified on combing dry hair or on rubbing, but a metal article like spoon does not. The charges on metal lead through our body to the ground as both are conductors of electricity. However, if a metal rod with a wooden or plastic handle is rubbed without touching its metal part, it shows signs of charging. Now, the next topic is basic properties of electric charge. We have seen that there are two types of charges, namely positive and negative, and their effects tend to cancel each other. Here we shall now describe some other properties of the electric charge. If the sizes of charged bodies are very small as compared to the distances between them, we treat them as point charges. All the charged content of the body is assumed to be concentrated at one point in space. Additivity of charges. This is the first basic property of electric charge. We have not as yet given a quantitative definition of a charge. We shall follow it up in the next section. We shall tentatively assume that this can be done and proceed. If a system contains two point charges Q1 and Q2, the total charge of the system is obtained simply by adding algebraically Q1 and Q2. That is, the charges add up like real numbers, or they are scalars like the mass of a body. If a system contains n charges Q1, Q2, Q3, etc. up to Qn, then the total charge of the system is Q1 plus Q2 plus Q3 plus and so on up to Qn. Charge has magnitude but no direction, similar to mass. However, there is one difference between mass and charge. Mass of a body is always positive, whereas charge can be either positive or negative. Proper signs have to be used while adding the charges in the system. For example, the total charge of a system containing 5 charges plus 1, plus 2, minus 3, plus 4 and minus 5 in some arbitrary unit is plus 1, plus 2, plus minus 3, plus 4, plus minus 5, that's equal to minus 1 in the same unit. The second basic property of electric charge is always conserved. We have already hinted to the fact that when bodies are charged by rubbing, there is a transfer of electrons from one body to the other. No new charges are either created or destroyed. A picture of particles of electric charge enables us to understand the idea of conservation of charge. When we rub two bodies, what one body gains in charge, the other body loses. Within an isolated system consisting of many charged bodies due to interactions among the bodies, charges may get redistributed, but it is found that the total charge of the isolated system is always conserved. Conservation of charge has been established experimentally. It is not possible to create or destroy a charge carried by any isolated system, although the charge-carrying particles may be created or destroyed in a process. This is the device which is used to detect charges on your body. And this device is called a gold leaf electroscope. Sometimes nature creates charged particles. A neutron turns into a proton and an electron. The proton and electron thus created have equal and opposite charges, and the total charge is zero before and after the creation. The next important basic property of electric charge is quantization of charge. Experimentally, it is established that all free charges are integral multiples of a basic unit of charge denoted by E. Thus, charge Q on a body is always given by Q equal to n times E, where n is any integer, positive or negative. This basic unit of charge is the charge that an electron or proton carries. By convention, the charge on an electron is taken to be negative. Therefore, charge on an electron is written as minus E and that on a proton as plus E. The fact that electric charge is always an integral multiple of E is termed as quantization of charge. There are a large number of situations in physics where certain physical quantities are quantized. The quantization of charge was first suggested by the experimental laws of electrolysis discovered by English experimentalist Faraday. It was experimentally demonstrated by Millikan in 1912. In the International System of Units, a unit of charge is called a coulomb and is denoted by a symbol C. A coulomb is defined in terms of the unit of electric current, which you are going to learn in a subsequent chapter. In terms of this definition, 1 coulomb is the charge flowing through a wire in 1 second if the current is 1 ampere. In this system, the value of the basic unit of charge is E is equal to 1.602192 into 10 power minus 19 coulomb. Thus, there are about 6 into 10 power 18 electrons in a charge of minus 1 coulomb. In electrostatics, charges of this large magnitude are seldom encountered, and hence we use smaller units, 1 microcoulomb, thus equal to 10 power minus 6 coulomb, or 1 millicoulomb, which is equal to 10 power minus 3 coulomb only. If the protons and electrons are the only basic charges in the universe, all the observable charges have to be integral multiples of E. Thus, if a body contains n1 electrons and n2 protons, the total amount of charge on the body is n2 times E plus n1 times minus E, which is equal to n2 minus n1 into E. Since n1 and n2 are integers, their difference is also an integer. Thus, the charge on any body is always an integral multiple of E and can be increased or decreased also in steps of E. The step size E is, however, very small because at the macroscopic level we deal with charges of a few microcoulombs. At this scale, the fact that charge of a body can increase or decrease in units of E is not visible. In this respect, the grainy nature of the charge is lost and it appears to be continuous. This situation can be compared with the geometrical concepts of points and lines. A dotted line viewed from a distance appears continuous to us but is not continuous in reality, as many points very close to each other normally give an impression of a continuous line. Many small charges taken together appear as a continuous charge distribution. At the macroscopic level, one deals with charges that are enormous compared to the magnitude of charge E. Since E is equal to 1.6 into 10 power minus 19 coulomb, a charge of magnitude, say 1 microcoulomb, contains something like 10 power 13 times the electronic charge. At this scale, the fact that charge can increase or decrease only in units of E is not very different from saying that charge can take continuous values. Thus, at the macroscopic level, the quantization of charge has no practical consequence and can be ignored. However, at the microscopic level, where the charges involved are of the order of a few tenths or hundredths of e, which they can be counted, they appear in discrete lumps and quantization of charge cannot be ignored. It is the magnitude of scale involved that is very important. Now, we are going to study about Coulomb's law. Coulomb's law is a quantitative statement about the force between two point charges. When the linear size of charged bodies are much smaller than the distance separating them, the size may be ignored and the charged bodies are treated as point charges. Coulomb has measured the force between two point charges and found that it varied inversely as the square of the distance between the charges and was directly proportional to the product of the magnitude of the two charges and acted along the line joining the two charges. Thus, if two point charges Q1 and Q2 are separated by a distance r in vacuum, the magnitude of the force between them is given by F is equal to Q into Q1 Q2 by r square. How did Coulomb arrive at this law from his experiments? Coulomb used a torsion balance for measuring the force between two charged metallic spheres, and the separation between two spheres is much larger than the radius of each sphere. The charged spheres may be regarded as point charges. However, the charges on the spheres were unknown to begin with. How then he could discover a relation like this expression? Coulomb thought of the following simple way. Suppose the charge on a metallic sphere is Q, and if the sphere is put in contact with an identical uncharged sphere, the charge will spread over the two spheres. By symmetry, the charge on each sphere will be Q by 2. Repeating this process, we can get charges Q by 2, Q by 4, etc. Coulomb varied the distance for a fixed pair of charges and measured the force for different separations. He then varied the charges in pairs, keeping the distance fixed for each pair. Comparing forces for different pairs of charges at different distances, Coulomb has arrived at the relation, which is given in equation 1.1. Coulomb's law, a simple mathematical statement, was initially experimentally arrived at in the manner described above. While the original experiments established it at a microscopic scale, it has also been established down to subatomic level, where the radius is of the order of 10 power minus 10 meter. Coulomb discovered this law without knowing the explicit magnitude of the charge. In fact, it is the other way around. Coulomb's law can now be employed to furnish a definition for a unit of charge. In the relation given in equation 1.1, k is so far arbitrary. We can choose any positive value of k. The choice of k determines the size of the unit of charge. In SI units, the value of k is about 9 to 10 power 9 nm square by c square. The unit of charge that results from this choice is called a coulomb, which we defined earlier. Putting this value of k in the equation 1.1, we see that for q1 is equal to q2 equal to 1 coulomb and r is equal to 1 meter, F is equal to 9 in 10 power 9 Newton. That is, 1 coulomb is the charge that when placed at a distance of 1 meter from another charge of the same magnitude in vacuum experiences an electrical force of repulsion of magnitude 9 into 10 power 9 Newton. One coulomb is evidently too big a unit to be used. So in practice, in electrostatics, you can use smaller units like 1 millicoulomb or 1 microcoulomb. The constant K in the equation 1.1 is usually put as K equal to 1 by 4 pi epsilon naught for later convenience, so that Coulomb's law is written as F is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square, where epsilon naught is called the permittivity of free space. The value of epsilon naught in SI units is epsilon is equal to 8.854 into 10 power minus 12 c square n power minus 1 m power minus 2. Since force is a vector, it is better to write Coulomb's law in the vector notation. Let the position vectors of charges q1 and q2 be r1 and r2 respectively. We denote force on q1 due to q2 by F12 and force on q2 due to q1 by F21. The 2-point charges q1 and q2 have been numbered 1 and 2 for convenience, and the vector leading from 1 to 2 is denoted by r21. So r21 is given by r2 minus r1. In the same way, the vector leading from 2 to 1 is denoted by r12, and r12 is given by r1 minus r2, thus equal to minus r21. The magnitude of the vectors r21 and r12 is denoted by r21 and r12 respectively, where r12 is equal to r21. The direction of a vector is specified by a unit vector along the vector. To denote the direction from 1 to 2 or from 2 to 1, we define the unit vectors as r21 is equal to r21 by r21, r12 cap is equal to r12 by r12, r21 cap minus r12 cap. Coulomb's force law between 2-point charges q1 and q2 located at r1 and r2 respectively is then expressed as F21 is equal to 1 by 4 pi epsilon naught q1 q2 by r21 square r21 unit vector. Some remarks on equation 1.3 are relevant. Equation 1.3 is valid for any sign of q1 and q2, whether positive or negative. If q1 and q2 are of the same sign, either both positive or both negative, F21 is along R21 cap, which denotes repulsion as it should be for like charges. If q1 and q2 are of opposite signs, F21 is along minus R21 cap, that is equal to R12 cap, which denotes attraction as expected for unlike charges. Thus, we do not have to write separate equations for the cases of like and unlike charges. Equation 1.3 takes care of both cases correctly. The force F12 on charge q1 due to charge q2 is obtained from equation 1.3 by simply interchanging 1 and 2, that is F12 equal to 1 by 4 pi epsilon naught q1 q2 by r12 square r12 cap, this is equal to minus F21. Thus Coulomb's law agrees with the Newton's third law. Coulomb's law, that is the equation 1.3, gives the force between two charges q1 and q2 in vacuum. If the charges are placed in matter or the intervening space has matter, the situation gets complicated due to the presence of charged constituents of matter. We shall consider electrostatics in matter in the next chapter. Now we shall consider about the forces between multiple charges. The mutual electric force between two charges is given by Coulomb's law. How to calculate the force on a charge where there are not one but several charges around. Consider a system of n stationary charges q1, q2, q3, etc. up to qn in vacuum. What is the force on q1 due to q2, q3 and so on up to qn? Coulomb's law is not enough to answer this question. Recall that forces of mechanical origin and according to the parallelogram law of additions. Is the same true for forces of electrostatic origin? Experimentally, it is verified that force on any charge due to a number of other charges is the vector sum of all the forces on that charge due to the other charges, taken one at a time. The individual forces are unaffected due to the presence of other charges. This is termed as the principle of superposition. To better understand the concept, and consider a system of three charges q1, q2 and q3 as shown in diagram 1.5. A. The force on one charge, say q1, due to two other charges q2, q3, can therefore be obtained by performing a vector addition of the forces due to each one of these charges. Thus, if the force on Q1 due to Q2 is denoted by F12, F12 is given by equation 1.3 even though other charges are present. Thus, F12 is equal to 1 by 4 pi epsilon naught Q1 Q2 by R12 square R12 cap. In the same way, the force on Q1 due to Q3 denoted by F13 is given by F13 equal to 1 by 4 pi epsilon naught Q1 Q3 by R13 square R13 cap, which again is the Coulomb force on Q1 due to Q3 even though other charge Q2 is present. Thus, the total force F1 on Q1 due to the two charges Q2 and Q3 is given as F1 is equal to F12 plus F13, that is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R12 square R12 cap plus 1 by 4 pi epsilon naught Q1 Q3 by R13 square R13 cap. The above calculation of force can be generalized to a system of charges more than 3 as shown in diagram 1.5b. The principle of superposition says that in a system of charges Q1, Q2, etc. up to Qn, the force on Q1 due to Q2 is the same as given by Coulomb's law. That is, it is unaffected by the presence of the other charges Q3, Q4, etc. up to Qn. The total force F1 on the charge Q1 due to all other charges is then given by the vector sum of the forces F12, F13, etc. up to F1n. That is, F1 is equal to F12 plus F13 plus and so on up to F1n. That's equal to 1 by 4 pi epsilon naught into Q1 Q2 by R12 square R12 cap plus Q1 Q3 by R13 square R13 cap plus and so on up to Q1 Qn by R1n square into R1n cap. That's equal to Q1 by 4 pi epsilon naught summation I equal to 2 to n Qi by R1i square into R1i cap. The vector sum is obtained as usual by the parallelogram law of addition of vectors. All of electrostatics is basically a consequence of Coulomb's law and the superposition principle. Electric field. Let us consider a point charge Q placed in vacuum at the origin O. If we place another point charge Q at a point P where OP equal to R, then the charge Q will exert a force on Q as per Coulomb's law. We may ask the question, if charge Q is removed, then what is left in the surrounding? Is there nothing? If there is nothing at the point P, then how does a force act when we place the charge Q at P? In order to answer such questions, the early scientists introduced the concept of field. According to this, we say that the charge Q produces an electric field everywhere in the surrounding. When another charge Q is brought at some point P, the field there acts on it and produces a force. The electric field produced by the charge Q at a point R is given as E of R is equal to 1 by 4 pi epsilon naught Q by R square R unit vector, that is equal to 1 by 4 pi epsilon naught Q by R square R cap, where R cap is equal to R by R is a unit vector from the origin to the point R. Thus, equation 1.6 specifies the value of the electric field for each value of the position vector R. The word field signifies how some distributed quantity, which could be a scalar or a vector, varies with position. The effect of the charge has been incorporated in the existence of the electric field. We obtain the force F exerted by a charge Q on a charge Q as F is equal to 1 by 4 pi epsilon naught Q times Q by R square R cap. Note that the charge Q also exerts an equal and opposite force on the charge Q. The electrostatic force between the charges Q and Q can be looked upon as an interaction between charge Q and the electric field of Q and vice versa. If we denote the position of charge Q by the vector R, it experiences a force F equal to the charge Q multiplied by the electric field E at the location of Q. Thus, F of R is equal to Q times E of R. Equation 1.8 defines the SI unit of electric field as Newton per Coulomb. Some important remarks may be made here. From equation 1.8, we can infer that if Q is unity, the electric field due to a charge Q is numerically equal to the force exerted by it. Thus, the electric field due to a charge q at a point in space may be defined as the force that a unit positive charge would experience if placed at that point. The charge q which is producing the electric field is called a source charge, and the charge q which tests the effect of a source charge is called a test charge. Note that the source charge q must remain at its original location. However, if a charge q is brought at any point around q, q itself is bound to experience an electrical force due to q and will tend to move. A way out of this difficulty is to make q negligibly small. The force F is then negligibly small, but the ratio F by Q is finite and defines the electric field. E is equal to limit Q tending to 0 F by Q. A practical way to get around the problem of keeping Q undisturbed in the presence of Q is to hold Q to its location by unspecified forces. This may look strange, but actually this is what happens in practice. When we are considering the electric force on a test charge Q due to a charged planar sheet, the charges on the sheet are held to their locations by the forces due to the unspecified charged constituents inside the sheet. Note that the electric field E due to Q, though defined operationally in terms of some test charge Q, is independent of Q. This is because F is proportional to Q, so the ratio F by Q does not depend on Q. The force F on the charge Q due to the charge Q depends on the particular location of charge Q, which may take any value in the space around the charge Q. Thus, the electric field E due to Q is also dependent on the space coordinate R. For different positions of the charge Q all over the space, we get different values of electric field E. The field exists at every point in three-dimensional space. Next one. For a positive charge, the electric field will be directed radially outwards from the charge. On the other hand, if the source charge is negative, the electric field vector at each point points radially inwards. Next, since the magnitude of the force F on charge Q due to charge Q depends only on the distance r of the charge Q from charge Q, the magnitude of the electric field E will also depend only on the distance r. Thus, at equal distances from the charge Q, the magnitude of its electric field E is the same. The magnitude of electric field E due to a point charge is thus same on a sphere with the point charge at its center. In other words, it has a spherical symmetry. Now we shall study about the electric field due to a system of charges. Consider a system of charges q1, q2, etc. up to qn with position vectors r1, r2, etc. up to rn related to some origin O. Like the electric field at a point in space due to a single charge, electric field at a point in space due to the system of charges is defined to be the force experienced by a unit test charge placed at that point, without disturbing the original positions of charges q1, q2 and so on up to qn. We can use Coulomb's law and the superposition principle to determine this field at a point P denoted by position vector r. Electric field E1 at R due to Q1 at R1 is given by E1 equal to 1 by 4 pi epsilon naught Q1 by R1p square R1p cap, where R1p cap is a unit vector in the direction from Q1 to P and R1p is the distance between Q1 and P. In the same manner, electric field E2 at R due to Q2 at R2 is E2 equal to 1 by 4 pi epsilon naught Q2 by R2p R2p square into R2p cap, where R2p cap is a unit vector in the direction from Q2 to P and R2p is the distance between Q2 and P. Similar expressions hold good for fields E3, E4, etc. up to En due to charges Q3, Q4, and etc. up to Qn. By the superposition principle, the electric field E at R due to the system of charges is as shown. Er equal to E1R plus E2R plus and so on up to ENR. That's equal to 1 by 4 pi epsilon naught Q1 by R1p square R1p cap plus 1 by 4 pi epsilon naught Q2 by R2p square R2p cap plus and so on up to 1 by 4 pi epsilon naught Qn by Rnp square Rnp cap. So E of R is equal to 1 by 4 pi epsilon naught summation I equal to 1 to n Qi by Rip square into Rip cap. E is a vector quantity that varies from one point to another point in space and is determined from the positions of the source charges. Next, we are going to study about the physical significance of electric field. You may wonder why the notion of electric field has been introduced here at all. After all, for any system of charges, the measurable quantity is the force on a charge, which can be directly determined using Coulomb's law and the superposition principle. Why then introduce this intermediate quantity called the electric field? For electrostatics, the concept of electric field is convenient but not really necessary. Electric field is an elegant way of characterizing the electrical environment of a system of charges. Electric field at a point in the space around a system of charges tells you the force a unit positive test charge would experience if placed at that point without disturbing the system. Electric field is a characteristic of the system of charges and is independent of the test charge that you place at a point to determine the field. The term field in physics generally refers to a quantity that is defined at every point in space and may vary from point to point. Electric field is a vector field since force is a vector quantity. The true physical significance of the concept of electric field, however, emerges only when we go beyond electrostatics and deal with time-dependent electromagnetic phenomena. Suppose we consider the force between two distant charges q1, q2 in accelerated motion. Now, the greatest speed with which a signal or information can go from one point to another is c, the speed of light. Thus, the effect of any motion of q1 on q2 cannot arise instantaneously. There will be some time delay between the effect force on q2 and the cause motion of q1. It is precisely here that the notion of electric field, strictly electromagnetic field, is natural and very useful. The field picture is this. The accelerated motion of charge q1 produces electromagnetic waves, which then propagate with the speed of light c, reach q2 and cause a force on q2. The notion of field elegantly accounts for the time delay. Thus, even though electric and magnetic fields can be detected only by their effects on charges, they are regarded as physical entities, not merely mathematical constructs. They have an independent dynamics of their own, that is, they evolve according to laws of their own. They can also transport energy, thus a source of time-dependent electromagnetic fields, turned on for a short interval of time and then switched off, leaves behind propagating electromagnetic fields, transporting energy. The concept of field was first introduced by Faraday and is now among the central concepts in physics. Electric field lines. We have studied electric field in the last section. It is a vector quantity and can be represented as we represent vectors. Let us try to represent E due to a point charge pictorially. Let the point charge be placed at the origin. Draw vectors pointing along the direction of the electric field with their lengths proportional to the strength of the field at each point. Since the magnitude of electric field at a point decreases inversely as the square of the distance of that point from the charge, the vector gets shorter as one goes away from the origin, always pointing radially outward. The figure 1.12 shows such a picture. In this figure, each arrow indicates the electric field, that is, the force acting on a unit positive charge placed at the tail of that arrow. Connect the arrows pointing in one direction and the resulting figure represents a field line. We thus get many field lines all pointing outwards from the point charge. Have you lost the information about the strength or magnitude of the field now because it was contained in the length of the arrow? No. Now the magnitude of the field is represented by the density of field lines. E is strong near the charge, so the density of field lines is more near the charge and the lines are closer. Away from the charge, the field gets weaker and the density of field lines is less, resulting in well-separated lines. Another person may draw more lines, but the number of lines is not important. In fact, an infinite number of lines can be drawn in any region. It is the relative density of lines in different regions which is important. We draw the figure on the plane of a paper, that is in 2 dimensions, but we live in 3 dimensions. So if one wishes to estimate the density of field lines, one has to consider the number of lines per unit cross-sectional area perpendicular to the lines. Since the electric field decreases as the square of the distance from a point charge and the area enclosing the charge increases as the square of the distance, the number of field lines crossing the enclosing area remains constant, whatever may be the distance of the area from the charge. We started by saying that the field lines carry information about the direction of electric field at different points in space. Having drawn a certain set of field lines, the relative density, that is closeness of the field lines at different points, indicates the relative strength of the electric field at those points. The field lines crowd where the field is strong and are spaced apart where it is weak. The figure 1.13 shows a set of field lines. We can imagine two equal and small elements of area placed at points R and S normal to the field lines there. The number of field lines in our picture cutting the area elements is proportional to the magnitude of the field at these points. The picture shows that the field at R is stronger than at S. To understand the dependence of the field lines on the area, or rather the solid angle subtended by an area element, let us try to relate the area with the solid angle, a generalization of angle to 3 dimensions. Recall how a plane angle is defined in 2 dimensions. Let a small transverse line element delta L be placed at a distance r from a point O. Then the angle subtended by delta L at O can be approximated as delta theta equal to delta L by r. Likewise, in 3 dimensions, the solid angle subtended by a small perpendicular plane area delta S at a distance r can be written as delta omega equal to delta S by r square. We know that in a given solid angle, the number of radial field lines is the same. In figure 1.13, for 2 points P1 and P2 at distances r1 and r2 from the charge, the element of area subtending the solid angle delta omega is r1 square delta omega at P1 and an element of area r2 square delta omega at P2 respectively. The number of lines, say n, cutting these area elements are the same. The number of field lines cutting unit area element is therefore n by r1 square delta omega at P1 and n by r2 square delta omega at P2 respectively. Since n and delta omega are common, the strength of the field clearly has a 1 by r square dependence. The picture of field lines was invented by Faraday to develop an intuitive non-mathematical way of visualizing electric fields around charge configurations. Faraday called them lines of force. This term is somewhat misleading, especially in case of magnetic fields. The more appropriate term is field lines, that is electric or magnetic, that we have adopted in this book. Electric field lines are thus a way of pictorially mapping the electric field around a configuration of charges. An electric field line is in general a curve drawn in such a way that the tangent to it at each point is in the direction of the net field at that point. An arrow on the curve is obviously necessary to specify the direction of electric field from the 2 possible directions indicated by a tangent to the curve. A field line is a space curve, that is, a curve in 3 dimensions. Figure 1.14 shows the field lines around some simple charge configurations. As mentioned earlier, the field lines are in 3-dimensional space, though the figure shows them only in a plane. The field lines of a single positive charge are radially outward, while those of a single negative charge are radially inward. The field lines around a system of 2 positive charges Q and Q give a vivid pictorial description of their mutual repulsion, while those around the configuration of 2 equal and opposite charges Q and minus Q, the dipole, show clearly the mutual attraction between the charges. The field lines follow some important general properties as given below. The field lines start from positive charges and end at negative charges. If there is a single charge, they may start or end at infinity. Next one is, in a charge-free region, the electric field lines can be taken to be continuous curves without any breaks. Then the next one is, 2 field lines can never cross each other. If they did, the field at the point of intersection will not have a unique direction which is absorbed. Then the last point is, electrostatic field lines do not form any closed loops. This follows from the conservative nature of electric field. Now we are going to study about the electric flux. Consider flow of a liquid with velocity v through a small flat surface ds in a direction normal to the surface. The rate of flow of liquid is given by the volume crossing the area per unit time VDS and represents the flux of liquid flowing across the plane. If the normal to the surface is not parallel to the direction of flow of liquid, that is to V, but makes an angle theta with it, the projected area in a plane perpendicular to V is delta ds cos theta. Therefore, the flux going out of the surface ds is V dot n cap ds. For the case of the electric field, we define an analogous quantity and call it electric flux. We should, however, note that there is no flow of a physically observable quantity, unlike the case of liquid flow. In the picture of electric field lines described above, we saw that the number of field lines crossing a unit area placed normal to the field at a point is a measure of the strength of electric field at that point. This means that we place a small planar element of area delta S normal to E at a point. The number of field lines crossing it is proportional to E delta S. Now suppose we tilt the area element by angle theta. Clearly, the number of field lines crossing the area element will be smaller. The projection of the area element normal to E is delta S cos theta. Thus, the number of field lines crossing delta S is proportional to E delta S cos theta. When theta equal to 90 degrees, the field lines will be parallel to delta S and will not cross it at all. That is given in figure 1.15. The orientation of area element and not merely its magnitude is important in many contexts. For example, in a stream, the amount of water flowing through a ring will naturally depend on how you hold the ring. If you hold it normal to the flow, maximum water will flow through it than if you hold it with some other orientation. This shows that an area element should be treated as a vector. It has a magnitude and also a direction. How to specify the direction of a plane area? Clearly, the normal to the plane specifies the orientation of the plane. Thus, the direction of a planar area vector is along its normal. How to associate a vector to the area of a curved surface? We imagine dividing the surface into a large number of very small area elements. Each small area element will be treated as planar and a vector associated with it as explained before. Notice one ambiguity here. The direction of an area element is along its normal, but a normal can point in two directions. Which direction do we choose as the direction of the vector associated with the area element? This problem is resolved by some convention appropriate to the given context. For the case of a closed surface, this convention is very simple. The vector associated with every area element of a closed surface is taken to be in the direction of the outward normal. This is the convention used in figure 1.16. Thus, the area element vector delta S at a point on a closed surface equals delta S n cap, where delta S is the magnitude of the area element and n cap is a unit vector in the direction of outward normal at that point. We now come to the definition of electric flux. Electric flux delta phi through an area element delta S is defined by delta phi equal to E dot delta S, which is equal to E delta S cos theta, which as seen before is proportional to the number of field lines cutting the area element. The angle theta here is the angle between E and delta S. For a closed surface with the convention stated already, delta is the angle between E and the outward normal to the area element. Notice we could look at the expression E delta S cos theta in two ways. E delta S cos theta, that is E times the projection of area normal to E. Or E perpendicular delta S, that is component of E along the normal to the area element times the magnitude of the area element. The unit of electric flux is nc power minus 1 m square. The basic definition of electric flux given by equation 1.11 can be used in principle to calculate the total flux through any given surface. All we have to do is to divide the surface into small area elements, calculate the flux at each element and add them up. Thus, the total flux phi through a surface S is given by phi is equal to summation E dot delta S. The approximation sign is put because the electric field E is taken to be a constant over the small area element. This is mathematically exact only when you take the limit delta S tends to 0 and the sum in equation 1.12 is written as an integral. Electric dipole. What is an electric dipole? An electric dipole is a pair of equal and opposite point charges plus q and minus q separated by a distance 2a. The line connecting the two charges defines the direction in space. By convention, the direction from minus q to q is said to be the direction of the dipole. The midpoint of locations of minus q and plus q is called the center of the dipole. The total charge of the electric dipole is obviously 0. This does not mean that the field of the electric dipole is 0. Since the charge plus q and minus q are separated by some distance, the electric fields due to them, when added, do not exactly cancel out. However, at distances much larger than the separation of the two charges, forming a dipole, in which case r is very much greater than 2a, the fields due to plus q and minus q nearly cancel out. The electric field due to a dipole therefore falls off at large distance faster than like 1 by r square, the dependence on r of the field due to a single charge plus q. These qualitative ideas are borne out by the explicit calculation as follows. The field of an electric dipole. The electric field of the pair of charges minus q and plus q at any point in space can be found out from Coulomb's law and the superposition principle. The results are simple for the following two cases: when the point is on the dipole axis and when it is in the equatorial plane of the dipole, that is, on a plane perpendicular to the dipole axis through its center. The electric field at any general point P is obtained by adding the electric fields E of minus q due to the charge minus q and E plus q due to the charge q by the parallelogram law of vectors. In the first case, for points on the axis, let the point be at a P at a distance r from the center of the dipole on the side of the charge q, as shown in figure 1.17a. Then E minus q is given by minus q by 4 pi epsilon naught r plus a the whole square into p, where p cap is the unit vector along the dipole axis from minus q to q. Also, E plus q is equal to q by 4 pi epsilon naught r minus a the whole square into p. The total field at P is given by E is equal to E plus Q plus E minus Q, and that's equal to Q by 4 pi epsilon naught into 1 by R minus A the whole square minus 1 by R plus A the whole square into P. That is given by Q by 4 pi epsilon naught into 4A by R square minus A square the whole square into P. For R very much greater than A, the expression for field electric field E is given by 4QA by 4 pi epsilon naught R cube into P cap, where r is very much greater than a. Now in the second case, for points on the equatorial plane, the magnitudes of the electric fields due to the two charges plus q and minus q are given by E plus q is equal to q by 4 pi epsilon naught into 1 by r square plus a square, and the field due to minus q is given by E minus q equal to q by 4 pi epsilon naught 1 by r square plus a square, and are equal. The directions of E plus q and E minus q are as shown in the diagram 1.17b. Clearly, the components normal to the dipole axis cancel away. The components along the dipole axis add up. The total electric field is opposite to P cap. We have the electric field E is given by minus of E plus q plus E minus q into cos theta P cap. That is given by minus 2qa by 4 pi epsilon naught into r square plus a square whole power 3 by 2 into p. At large distances, r is greater than a, this reduces to E equal to minus 2qa by 4 pi epsilon naught r cube into p cap, and r is very much greater than a. From the equations 1.15 and 1.18, it is clear that the dipole field at large distances does not involve q and a separately. It depends on the product qa. This suggests the definition of dipole moments. The dipole moment vector p of an electric dipole is defined by p equal to q into 2a in p cap. That is, it is a vector whose magnitude is charge q times the separation 2a between the pair of charges plus q and minus q. The direction is along the line from minus q to plus q. In terms of P, the electric field of a dipole at large distances takes simple forms. At a point on the dipole axis, E is given by 2p by 4 pi epsilon naught r cube. for the case r very much greater than a, and at a point on the equatorial plane E is equal to minus P by 4 pi epsilon naught r cube, and here also r is very much greater than a. Notice the important point that the dipole field at large distances falls off not as 1 by r square but as 1 by r cube. Further, the magnitude and the direction of the dipole field depends not only on the distance r but also on the angle between the position vector r and the dipole moment p. We can think of the limit when the dipole size 2a approaches 0. The charge q approaches infinity in such a way that the product p is equal to q into 2a is finite. Such a dipole is referred to as a point dipole. For a point dipole, equations 1.20 and 1.21 are exact true for any r. What is the physical significance of dipoles? In most molecules, the centers of positive charges and of negative charges lie at the same place. Therefore, the dipole moment is zero. Carbon dioxide and methane are of this type of molecules. However, they develop a dipole moment when an electric field is applied. But in some molecules, the centers of negative charges and of positive charges do not coincide. Therefore, they have a permanent electric dipole moment even in the absence of an electric field. Such molecules are called polar molecules. Water molecules, that is H2O, is an example of this type. Various materials give rise to interesting properties and important applications in the presence or absence of electric field. Dipole in a uniform magnetic field. Let us consider a permanent dipole of dipole moment P in a uniform external field E, as shown in the diagram. By permanent dipole, we mean that P exists irrespective of E, it has not been induced by E. There is a force QE on Q and a force minus QE on minus Q. The net force on the dipole is zero since E is uniform. However, the charges are separated, so the forces act at different points, resulting in a torque on the dipole. When the net force is zero, the torque, that is the couple, is independent of the origin. Its magnitude equals the magnitude of each force multiplied by the arm of the couple, which is perpendicular distance between the two antiparallel forces. Magnitude of the torque is given by QE into 2A sin theta, that is given by 2QA E sin theta. Its direction is normal to the plane of the paper coming out of it. The magnitude of P cross E is also P sin theta and its direction is normal to the paper coming out of it. Thus, the torque tau is equal to P cross E. This torque will tend to align the dipole with the field E. When P is aligned with E, the torque is zero. Now, let us consider the case if the field is not uniform. In that case, the net force will be evidently non-zero. In addition, there will be, in general, a torque on the system as before. The general case is involved, so let us consider the simple situations when P is parallel to E or antiparallel to E. In either case, the net torque is zero, but there is a net force on the dipole if E is not uniform. It is easily seen that when P is parallel to E, the dipole has a net force in the direction of increasing field. When P is antiparallel to E, the net force on the dipole is in the direction of decreasing field. In general, the force depends on the orientation of P with respect to E. This brings us to a common observation in frictional electricity. A comb run through dry hair attracts pieces of paper. The comb acquires charge through friction, but the paper is not charged. What then explains the attractive force? This is taken from the previous discussion. That is, the charged comb polarizes the piece of paper, that is, induces a net pole dipole moment in the direction of the field. Further, the electric field due to the comb is not uniform. This non-uniformity of the field makes a dipole to experience a net force on it. In this situation, it is easily seen that the paper should move in the direction of the comb. Now, we are going to study about the continuous charge distribution. We have so far dealt with charge configurations involving discrete charges Q1, Q2, Q3, etc. up to Qm. One reason why we restricted to discrete charges is that the mathematical treatment is simpler and does not involve calculus. For many purposes, however, it is impractical to work in terms of discrete charges and we need to work with continuous charge distributions. For example, on the surface of a charged conductor, it is impractical to specify the charge distribution in terms of the locations of the microscopic charged constituents. It is more feasible to consider an area element delta S on the surface of the conductor, which is very small on the macroscopic scale but big enough to include a very large number of electrons, and specify the charge delta Q on that element. We then define a surface charge density sigma at the area element by sigma equal to delta Q by delta S. We can do this at different points on the conductor and thus arrive at a continuous function sigma called the surface charge density. The surface charge density sigma, so defined, ignores the quantization of charge and the discontinuity in charge distribution at the microscopic level. Sigma represents macroscopic surface charge density, which in a sense is a smoothed out average of the microscopic charge density over an area element delta S, which, as said before, is large microscopically but small macroscopically. The units for sigma are coulomb per meter square, since the surface charge density is given by charge per unit area. Similar considerations apply for a line charge distribution and a volume charge distribution. The linear charge density lambda of a wire is defined by lambda equal to delta Q by delta L, that is the charge per unit length, where delta L is a small line element of wire on the macroscopic scale. That, however, includes a large number of microscopic charged constituents, and delta Q is the charge contained in that line element. The units for lambda are coulomb per meter. The volume charge density, it is also called as charge density, is defined in a similar manner, that is given by rho equal to delta Q by delta V, where delta Q is the charge included in the macroscopically small volume element delta V that includes a large number of microscopic charged constituents. The units for rho are coulomb per meter cube, because this is the charge per unit volume. The notion of continuous charge distribution is similar to that we adopt for continuous mass distribution in mechanics. When we refer to the density of a liquid, we are referring to its macroscopic density. We regard it as a continuous fluid and ignore its discrete molecular constitution. Then, the field due to a continuous charge distribution can be obtained in much the same way as for a system of discrete charges. The equation: suppose a continuous charge distribution in space has a charge density ρ. Choose any convenient origin O and let the position vector of any point in the charge distribution be r. The charge density ρ may vary from point to point, that is, it is a function of r. Divide the charge distribution into small volume elements of size delta V. The charge in a volume element delta V is rho AV, that is rho delta V. Now consider any general point P inside or outside the distribution with position vector r. The electric field due to the charge rho delta V is given by Coulomb's law, that is delta E equal to 1 by 4 pi epsilon naught rho delta V by r square r unit vector, where r dash is the distance between the charge element and P, and r dash unit vector is the unit vector in the direction from the charge element to P. By the superposition principle, the total electric field due to the charge distribution is obtained by summing over electric fields due to different volume elements. So E is equal to 1 by 4 pi epsilon naught summation all delta V rho delta V by r dash square into r dash unit vector. Here we can note that rho, r dash and r dash unit vector all can vary from point to point. In a strict mathematical method, we should let delta V tending to 0 and the sum then becomes an integral. But we omit that discussion here for simplicity. In short, using Coulomb's law and the superposition principle, electric field can be determined for any charge distribution, discrete or continuous, or part discrete and part continuous. Next we are going to study about the Gauss law. A simple application of the notion of electric flux, let us consider the total flux through a sphere of radius r, which encloses a point charge q at its center. We can divide the sphere into small area elements as shown. The flux through an area element delta S is given by delta phi equal to E dot delta S, and that is given by q by 4 pi epsilon naught r square into r unit vector dot delta S, where we have used Coulomb's law for the electric field due to a single charge q. The unit vector r cap is along the radius vector from the center to the area element. Now, since the normal to a sphere at every point is along the radius vector at that point, the area element delta s on r cap have the same direction. Therefore, delta phi equal to q by 4 pi epsilon naught r square into delta s. Since the magnitude of a unit vector is 1, the total flux through the sphere is obtained by adding up the flux through all the different area elements. Phi equal to summation all delta s q by 4 pi epsilon naught r square delta s. Since each area element of the sphere is at the same distance r from the charge, phi is given by q by 4 pi epsilon naught r square summation all delta s into delta s, that will be equal to q by 4 pi epsilon naught r square into s. Now s, the total area of the sphere, equals 4 pi r square. Thus phi equal to q by 4 pi epsilon naught r square into 4 pi r square, that's given by q by epsilon naught. This equation is a simple illustration of a general result of electrostatics called Gauss law. So we state Gauss law without proof as electric flux through a closed surface S is equal to q by epsilon naught, where q is total charge enclosed by S. The law implies that the total electric flux through a closed surface is zero if no charge is enclosed by the surface. You can see that explicitly in the simple situation. Here the electric field is uniform and we are considering a closed cylindrical surface with its axis parallel to the uniform field E. The total flux phi through the surface is phi equal to phi 1 plus phi 2 plus phi 3, where phi 1, phi 2 represent the flux through the surfaces 1 and 2 of the circular cross-section of the cylinder, and phi 3 is the flux through the curved cylindrical part of the closed surface. Now the normal to the surface 3 at every point is perpendicular to E, so by definition of flux phi 3 will be equal to 0. Further, the outward normal to E is along E, while the outward normal to 1 is opposite to E. Therefore, phi 1 equal to minus E S1, phi 2 equal to plus E S2, S1 will be equal to S2 equal to S, where S is the area of circular cross-section. Thus, the total flux is 0 as expected by Gauss law. Thus, whenever you find that the net electric flux through a closed surface is 0, we conclude that the total charge contained in the closed surface is 0. The great significance of Gauss law is that it is true in general and not only for the simple cases we have considered above. Let us note some important points regarding this law. Gauss law is true for any closed surface, no matter what its shape or size. The term Q on the right side of Gauss law includes the sum of all charges enclosed by the surface. The charges may be located anywhere inside the surface. In the situation when the surface is so chosen that there are some charges inside and some outside, the electric field, whose flux appears on the left side of the equation, is due to all the charges, but both inside and outside S. The term Q on the right side of Gauss law, however, represents only the total charge inside S. The surface that we choose for the application of Gauss law is called the Gaussian surface. We may choose any Gaussian surface and apply Gauss law. However, take care not to let the Gaussian surface pass through any discrete charge. This is because electric field due to a system of discrete charges is not well defined at the location of any charge. As it goes close to the charge, the field grows without any bound. However, the Gaussian surface can pass through a continuous charge distribution. Gauss law is often useful towards a much easier calculation of the electrostatic field when the system has some symmetry. This is facilitated by the choice of a suitable Gaussian surface. Finally, Gauss law is based on the inverse square dependence on distance contained in the Coulomb's law. Any violation of Gauss law will indicate departure from the inverse square law. Applications of Gauss law. The electric field due to a general charge distribution is given by equation 1.27. In practice, except for some special cases, the summation or integration involved in this equation cannot be carried out to give electric field at every point in space. For some symmetric charge configurations, however, it is possible to obtain the electric field in a simple way using the Gauss law. Now, let us consider some examples. First one being the field due to an infinitely long straight uniformly charged wire. For this, we consider an infinitely long thin straight wire with uniform linear charge density lambda. The wire is obviously an axis of symmetry. Suppose we take the radial vector from O to P and rotate it around the wire. The points P, P dash, P double dash so obtained are completely equivalent with respect to the charged wire. This implies that the electric field must have the same magnitude at these points. The direction of electric field at every point must be radial, outward if lambda is greater than 0 and inward if lambda is less than 0. Consider a pair of line elements P1 and P2 of the wire as shown. The electric fields produced by the two elements of the pair when summed give a resultant electric field which is radial. The components normal to the radial vector cancel. This is true for any such pair and hence the total field at any point P is radial. Finally, since the wire is infinite, electric field does not depend on the position of P along the length of the wire. In short, the electric field is everywhere radial in the plane cutting the wire normally, and its magnitude depends only on the radial distance r. To calculate the field, imagine a cylindrical Gaussian surface as shown in the diagram. Since the field is everywhere radial, flux through the two ends of the cylindrical Gaussian surface is 0. At the cylindrical part of the surface, E is normal to the surface at every point and its magnitude is constant. Since it depends only on r, the surface area of the curved part is 2 pi r L, where L is the length of the cylinder. Flux through the Gaussian surface is equal to flux through the curved cylindrical part of the surface. That is given by E into 2 pi r L. The surface includes charge equal to lambda times L, and Gauss law then gives E into 2 pi r L equal to lambda L by epsilon naught, that is E equal to lambda by 2 pi epsilon naught r. Vectorially, E at any point is given by E equal to lambda by 2 pi epsilon naught r n cap, where n cap is the radial unit vector in the plane normal to the wire passing through the point. E is directed outward if lambda is positive and inward if lambda is negative. Note that when we write a vector A as a scalar multiplied by a unit vector, that is as A equal to A into A cap, the scalar A is an algebraic number. It can be negative or positive, and the direction of A will be the same as that of the unit vector A cap if A is greater than 0 and opposite to A cap if A is less than 0. When you want to restrict the non-negative values, we use the symbol modulus A and call it the modulus of A, thus modulus of A is greater than or equal to 0. You can also note that though only the charge enclosed by the surface lambda L was included above, the electric field is due to the charge on the entire wire. Further, the assumption that the wire is infinitely long is crucial. Without this assumption, we cannot take E to be normal to the curved part of the cylindrical Gaussian surface. However, the equation 1.32 is approximately true for electric field around the central portions of a long wire, where the end effects may be ignored. The next application of Gauss law is the field due to a uniformly charged infinite plane sheet. Let sigma be the uniform surface charge density of an infinite plane sheet. We take the x-axis normal to the given plane. By symmetry, the electric field will not depend on y and z coordinates, and its direction at every point must be parallel to the x direction. We can take the Gaussian surface to be a rectangular parallelepiped of cross-sectional area A as shown. A cylindrical surface will also do it. As seen from the figure, only two faces 1 and 2 will contribute to the flux. Electric field lines are parallel to the other faces and they therefore do not contribute to the total flux. The unit vector normal to surface 1 is in minus x direction, while the unit vector normal to surface 2 is in the plus x direction. Therefore, flux E dot delta S through both the surfaces are equal and add up. Therefore, the net flux through the Gaussian surface is 2EA. The charge enclosed by the closed surface is sigma A. Therefore, by Gauss law, you can write E is equal to sigma by 2 epsilon naught. So, by Gauss law, E is equal to sigma by 2 epsilon naught, and vectorially it can be represented as E equal to sigma by 2 epsilon naught into n cap, where n cap is the unit vector normal to the plane and going away from it. E is directed away from the plate if sigma is positive and towards the plate if sigma is negative. You can note that the above application of the Gauss law has brought out an additional fact, that is, E is independent of x also. For a finite larger planar sheet, equation 1.33 is approximately true in the middle regions of the planar sheet away from the ends. Now the third application of Gauss law is to find out the field due to a uniformly charged thin spherical shell. For this, let sigma be the uniform surface charge density of a thin spherical shell of radius capital R. The situation has obvious spherical symmetry. The field at any point P outside or inside can depend only on R, the radial distance from the center of the shell to the point, and must be radial, that is, along the radius vector. Field outside the shell. Consider a point P outside the shell with radius vector R. To calculate E at P, we take the Gaussian surface to be a sphere of radius R and with center O, passing through point P. All the points on this sphere are equivalent relative to the given charged configuration. This is what we mean by spherical symmetry. The electric field at each point E and is along the radius. The electric field at each point of the Gaussian surface has the same magnitude E and is along the radius vector at each point. Thus, E and delta S at every point are parallel, and the flux through each element is E delta S. Summing over all delta S, the flux through the Gaussian surface is E times 4 pi r square, and the charge enclosed is sigma into 4 pi r square. So by Gauss law, E into 4 pi r square equal to sigma by epsilon naught 4 pi capital R square, where E is given by sigma r square by epsilon r square, that can be written as q by 4 pi epsilon naught r square, where q is the equal to 4 pi r square sigma is the total charge on the spherical shell. Vectorially, we can represent this as E equal to q by 4 pi epsilon r square, or unit vector. The electric field is directed outward if q is greater than 0 and inward if q is less than 0. This, however, is exactly the field produced by a charge placed at the center O. Thus, for points outside the shell, the field due to a uniformly charged shell is as if the entire charge of the shell is concentrated at its center. And we can consider the second case, that is the field inside the shell. So here, in this case, the point P is inside the shell, and the Gaussian surface is again a sphere through point P centered at O. The flux through the Gaussian surface calculated as before is E into 4 pi r square. However, in this case, the Gaussian surface encloses no charge, and Gauss law then gives E into 4 pi r square equal to 0, that is, E is equal to 0 if R is less than capital R. That is, the field due to a uniformly charged thin shell is 0 at all points inside the shell. This important result is a direct consequence of Gauss law, which follows from Coulomb's law. The experimental verification of this result confirms the 1 by r square dependence in Coulomb's law.